First of all, thank you to Christina and the whole Science in the Break team for the invitation. I'm going to talk to you today about how we measure muscle fiber lengths using magnetic resonance imaging and diffusion tensor imaging. So there's a whole bunch of reasons why we would want to measure muscles and study muscles and how we can move, and also sometimes how they kind of hinder our movement a little bit. You can see some really nice images here from Vesalius, who did this a long time ago. And obviously, if we would walk around like we can see in these images, it would be much easier for us scientists because the muscles are right there and we can just look at them. Now, obviously, this isn't the case. We have lots of other surrounding tissues. We've got fat layers, we've got skin, and so on. A long time ago already, people had lots of interest in how these muscles looked like, what they were designed like, how their anatomy consisted of. So then again, we can't really keep using cadavers because there's lots of limitations with that. I'm not going to go into detail now, but so other techniques have started coming. So on the left hand, you can again see a cadaver image from Norici et al., where you can nicely see the fibers. So you can see that the fibers in the muscle are angled at a certain angle, and they connect between two sheets of usually aponeuroses or tendon. So the red line that I've drawn here is how we measure fiber length, and then we can also measure this angle at which the fibers attach to these tissues. Now on the right, one of the first successful attempts where they used ultrasound imaging to look at this in vivo in humans. Again, on the right, you can see that I've drawn the fascicle with red, so you can nicely see these white lines and the black lines on the ultrasound image that show our muscle fibers. And on the bottom, you can see the same muscle, the same participant, but during contraction state. And so if we overlap these two, you can clearly see that the fascicle has shortened and it's changed its angle. So obviously that's really cool if we can do this when humans are still alive and we ask them to do certain tasks. So here's a really nice example of one of my good friends, Martino Franchi, where they did a review on some of these methods and how we can measure muscle fiber lengths. On the left, you can see a beautiful image where, again, in orange, you can see the fiber lengths really nicely. And on the right, they used a panoramic image, panoramic ultrasound image. It's basically the same as what your iPhone does. If your view is too small and you want to make a nice wide picture, you can use these techniques. One of the problems, though, with ultrasound is that we're still limited to a 2D image, and you've got ways to do 3D ultrasound, but there's lots of limitations with that as well for these kind of measurements. One other, for example, limitation is that we're restricted to the more superficial muscles usually, and it's a bit harder to study deeper lying muscles or a lot of muscles. So that's where diffusion tensor imaging is a really promising technique. And here we can see one of the first examples of that in the paper by Damon and al., where they looked at a red muscle, and in red you can nicely see a reconstruction of the muscle fiber bundle. And then on the right is a beautiful figure by one of my other good friends, Bart Bolsterle, who did some beautiful work here in trying to reconstruct muscle fibers in humans. So this is a medial gastrocnemius, a human calf muscle, where in blue you can see the fibers reconstructed, and then on the image all the way on the right in B, he grouped these fibers into fiber bundles. And so these red lines represent these fiber bundles. And you can clearly see that we can get a nice idea of the orientation of these fibers. And if we do some extrapolation to the boundaries of the muscle, which you can see here in gray, we can easily get fiber lengths. And that's exactly what we did in this project. So what we first do is we use the magnetic resonance imaging to get the muscle shape out. So basically what's surrounding the muscle and the muscle, its shape. So that's what we did here in yellow. So basically we go through each of the slices on the MRI and we highlight which muscle that we're interested in. Then we stitch this all together and we get a nice example like we can see in here. And I've got this video here. I'm just gonna rotate the muscle around a little bit just to get you a good idea of what you're actually looking at. And so if you look at the left still, on the top, this is the most proximal part of the muscle. So this is closest to your knee. And then on the bottom, we've got the distal part of the muscle, so closer to your ankle. And this is basically the image that you're going to see a lot throughout the rest of my presentation. So we basically took one slice to see, okay, this is where the muscle fibers can attach, and this is where we can measure muscle fiber lengths. So now we'll introduce the muscle fiber lengths on the right. You can see them here nicely in red. Take into account that this is maybe 100 fibers or so. We have a lot more measurements. We usually measure a few thousand fibers, but I only imaged a few, well, because this is, I think, maybe 1,000, so obviously it becomes really hard to see anything on it. And so we tried to take an approach where we wanted to see, are there regional muscle fiber lengths? So is in one region of the muscle, maybe are the fibers longer there, whereas in another, maybe they're shorter there. And this has a lot of functional consequences. So we wanted to see if we can do this with our DTI approach. And for that, we obviously have to say that a muscle fiber is in a certain region, but as you could see, they're quite long. So it's quite hard to say to which region exactly a fiber belongs. So what we did is we took the midpoints of the fibers, which you can see here on this slide. So again, I've taken maybe 10 fibers or so in red, and then on the black, I've highlighted the midpoint. So the midpoint is exactly what it says. It's just the middle of the fiber. And then we do this with all of the fibers that we have. Like I said, we have a lot, and that's what's shown on the right. So all these black little dots, they are the midpoints of all of the fibers that we've reconstructed in this participant, in this calf muscle. Now it's important to already immediately say that these are not all the fibers in the muscle, so you can clearly see that there are gaps, but it's the fibers that with our technique we were able to reconstruct. And there's a whole bunch of reasons why in certain areas we can't pick up fibers, often because there's other tissues or there's intramuscular fat or so on. But this is obviously one very, very important, let's say, limitation of the DTI, because this is very dependent on individual anatomy. So you can see here in the red circles that there's areas where we will have a lot of fibers together. They appear as darker areas, and there's areas in the muscle where we don't pick up any fibers at all. Now, obviously, if we compare two participants like we did here, we can see that there's a lot of difference between that. So the areas where it's darker, more fiber midpoints are closer to each other. They're completely in a different area in the muscle than in the other participant. And if I compare the two areas in blue, for example, in the participant on the left, we have almost no fibers, whereas on the right, we have a lot of fibers. Now, this is important because if we just say, okay, we're going to take an average of the whole muscle or of a specific region of the muscle, if one participant has a lot more fibers in that region, then obviously it's going to be biased more heavily towards that region. Whereas if another participant only has a few fibers there and a lot more fibers somewhere else, it's going to be biased towards that region where there's more muscle fibers there. So what we did is we tried to divide the region, the muscle into different regions, and then we calculated the median fiber lengths in those regions, just to take into account this limitation a little bit. Just again, the image that you're going to see a lot is this plane where you look right onto the muscle. Let's say if you're looking from someone from behind, you look at their calf muscles. We cut the top part of the muscle because we didn't have data there on the DTI because we're limited to a certain field of view. So we can't measure, let's say, the entire leg with this technique yet. And then we split the muscle into all of these smaller regions, as you can see on the right. So in blue, I split the muscle into these small rectangles, and then we looked at all of the midpoints within one rectangle, took the median fiber length, and then we did this for all these regions to get an idea of what the fiber length is in these muscle regions. And so we wanted to compare different sizes of muscle regions, because obviously if we have smaller regions, it's more interesting because we can really look into detail at very local areas of the muscle. But again, there's some limitations and it becomes much harder to have a reliable reconstruction of the muscle fibers there. So we compared these 4 different sizes and just tell you, you'll have to believe me or read the paper, that the large region sizes are the better. They're more reliable for these kind of measurements. For all the large regions of all our participants, we looked at each region and we basically looked at the reliability in each of those regions just to get an idea of can we, in all of the regions of the muscle, can we reliably get these muscle fiber lengths at. In blue, these are all the regions that we can say we're quite sure that there's a reliable measure of muscle fiber lengths there. In yellow, we weren't very confident. For example, here in this region, you can see that the intraclass correlation, which is a measure of how reliable a measurement is very high. It's based on all 8 participants and a high number of fibers, almost on average 850 fibers. Whereas in other regions, you can see here that the correlation is quite low, it's not very reliable. And then other regions, like you can see on the top, for example, the ICC is not too bad, but it's only based on a low number of participants, a low number of fibers. So we couldn't really confidently say that we have enough data to make this reliability measure, let's say, reliable. What we did here is we took all of the blue regions and then we applied this to our big data sets. And we had this for two muscles. So on the left, we have the lateral gastrocnemius. On the right, we have the medial gastrocnemius. So the two most proximal big calf muscles. And so you can see that some of the areas overlap, but there are certain regions where it's not very reliable in one muscle, but it is in the other muscle. And so then we applied this to a larger data set of 32 healthy participants, young and old, male and female. And here you can look at the fiber length. So in this region, for example, in the lateral gastrocnemius muscle, you can see that we have an average fiber length over all of those participants of around 86 millimeters. Now also pay attention and see that there's a really large variation among all of the participants. So there's quite a lot of variability between people. There's other regions where before we had around 85, now we have 55 millimeters. So already not a very large muscle. You can see that there's already quite a bit of variation. So there is some evidence of regional architecture, of regional differences in muscle fiber lengths. So if we look at the whole muscle, you can see that, for example, more distally, so more towards the ankle on the bottom here, we got rather short fiber lengths. And in other areas, we have much larger fiber lengths. But again, there's a lot of variation between people as well as between the regions. And we found the same for the medial gastrocnemius. So regions where we have long fiber lengths, regions where we have less long fiber lengths, and a lot of variation between participants. So this is kind of an advertisement also for saying that it's really important to look also at individual differences and to look at an individual basis when you're thinking about deciding muscle function and so on. So with that, I want to thank again the Science in the Break team, and I want to thank all of my awesome co-authors for all their help in this awesome project.